Dear students, in continuation with theorems on limits, the next result is squeeze principle. If a n, b n and c n are three sequences such that every term of b n is between a n and c n for all n, and second sequence a n and c n both converges to a, then b n also converges to a. Now the proof is, let epsilon greater than 0 be any given number. Since a n converges to a and c n converges to a, therefore there exist positive integers m1 and m2 such that, using definitions for convergence here, a n minus a mod value will be less than epsilon for all n greater than equal to m1. cn minus a mod value will be less than epsilon for all n greater than equal to m2. For these two relations, if we choose or let m is maximum of m1 and m2, therefore an minus a mod value will be less than epsilon and cn minus a mod value will be less than epsilon for all those n which are greater than equal to m. This implies an is between a minus epsilon to a plus epsilon, and cn is also a minus epsilon to a plus epsilon for all n greater than equal to m. But it is given that bn is between an and cn. Therefore, by above we are able to say bn will also be between a minus epsilon to a plus epsilon for all n greater than equal to m. Or rewrite, that is bn is between a minus epsilon to a plus epsilon. Therefore bn minus a mod value will be less than epsilon for all n greater than equal to m. Therefore we can say bn converges to a. Now next result, Cauchy's first theorem on limits. If a sequence an converges to a and bn is equal to sum of n terms divided by n, then the sequence bn also converges to a. Important result. Taking the proof. For the proof, let cn is equal to an minus a for all n belongs to n. Therefore, limit when n tends to infinity for cn is equal to limit n tends to infinity on an minus a, which is equal to 0. bn is equal to a1 plus a2 plus a3 plus an by n. Putting the value for a1, a2, a3, an here, we have value is c1 plus a, c2 plus a, cn plus a by n. Therefore this becomes na plus c1 plus c2 c3 plus cn by n, or this becomes a plus c1 plus c2 plus cn by n, marking this as number 1. Let epsilon greater than 0 be any given number. Since cn converges to 0, therefore there exists m belongs to n such that cn minus epsilon mod value will be less than epsilon by 2 for all n greater than equal to m. Also cn is bounded, since every convergent sequence is bounded sequence. Therefore there exists positive number k such that cn mod is less than k for all n belongs to n. Thus for all n greater than equal to m, we have c1 plus c2 plus so on cn by n minus 0 mod value will be equal to c1 plus c2 plus cn by n mod value. Using identities here, separating the mod value becomes greater than. Now value becomes 1 by n, c1 mod plus c2 mod plus cn mod, and we can also write down, that is c1 plus c2 mod plus cm mod, cm plus 1 mod, and so on cn mod. That is c1 to cm, this is m terms k times, and cm plus 1 to Cn. This is n minus m times term. Making addition, the identity becomes km by n plus epsilon into n minus m by 2n. Therefore, C1 plus C2 plus Cn minus 0 by 0 mod less than km by n plus epsilon n minus m by 2n, marking this as number 2. Now, km by n is less than epsilon by 2 if n by km is greater than 2 by e, that is if n is greater than 2 km by epsilon, marking this as number 3. And epsilon into n minus m by 2n is less than epsilon by 2 if n minus m by n is less than 1, that is if n minus m is less than n, that is if m is greater than 0, marking this as number 4. Let m be a positive integer such that m equal to maximum of m and 2 km by epsilon. Now using third and fourth in second, we have c1 plus c2 plus cn by n minus 0 mod becomes less than epsilon by 2 plus epsilon by 2 for all n greater than equal to m. Therefore, c1 plus c2 plus cn by n minus 0 mod becomes less than epsilon for all n greater than equal to m, and this is the definition for convergence sequence c1 plus c2 plus cn by n converges to 0. Using fifth in first, we have that Bn converges to A, or A1 plus A2 plus An by n converges to A, hence the result. Remark: the converse of the above theorem is not always true. Consider An is equal to minus 1 raised to power n for all n. Therefore, A1 is minus 1, A2 is 1, A3 is minus 1, An is minus 1 raised to power n. Let Bn equal to A1 plus A2 plus An by n. Value becomes Bn becomes 0 if n is even and minus 1 by n if n is odd. Limiting value of Bn becomes 0 and so Bn converges. Thus we have A1 plus A2 plus An by n is convergent sequence, but An is not convergent. Now the next theorem: if An is a sequence of positive terms converging to A greater than 0 and Bn is equal to A1 into A2 into An raised to power 1 by n, then Bn converges to A. Taking the proof, let Cn is equal to log of An. This implies Cn converges to log of A as An converges to A. Therefore, by Cauchy first theorem on limits, we have limiting value when n tends to infinity of C1 plus C2 plus Cn by n is equal to logarithm of A. Or limiting value when n tends to infinity log A1 plus log A2 plus log An by n is equal to log A. Or limit n tends to infinity 1 by n using logarithm, where logarithm of A1 into A2 into An is becomes log A. Or limiting value of log of A1 A2 An raised to power 1 by n is equal to log A. Taking anti-log on both sides, limit n tends to infinity A1 into A2 into An raised to power 1 by n equal to A. Thus Bn converges to A. Now the next result, Cauchy's second theorem on limits. If An is a sequence of positive terms and limit of An raised to power 1 by n when n tends to infinity, and limiting value of An plus 1 by An when n tends to infinity both exist finitely or infinitely, then limiting value of An raised to power 1 by n when n tends to infinity will be equal to limiting value of An plus 1 by An when n tends to infinity. For the proof, we are firstly suppose that limit of An plus 1 by An when n tends to infinity equal to L. Case first, when L is finite as limiting value is equal. Therefore, using the definition here, for a given epsilon there exists a positive integer m such that an plus 1 divided by an minus l mod value will be less than epsilon by 2 for all n greater than equal to m, or an plus 1 by an is between l minus epsilon by 2 to l plus epsilon by 2, marking this as number 1. Putting n is equal to m plus 1 to n minus 1 in number 1, we get these identities. Last one is, and these are n minus m inequalities. Multiplying the above n minus m inequalities, we have result as l minus epsilon by 2 raised to power n minus m less than an by am is less than l plus epsilon by 2 raised to power n minus m. Now cross multiplying by am on both sides, we have identities is equal to, that is this one, marking this as number 2. Now limiting value of am raised to power 1 by n l minus epsilon by 2 raised to power 1 minus m by n, limiting value n tends to infinity is equal to 1 into l minus epsilon by 2, and limiting value of am raised to power 1 by n l plus epsilon by 2 raised to power 1 minus m by n, limiting value n tends to infinity is equal to 1 into l plus epsilon by 2. Therefore, given epsilon greater than 0, there exist positive integers m1 and m2 such that both inequalities hold. If we suppose that let m equal to maximum of m1 m2, therefore for all n greater than equal to m, we have these two identities, marking this as number 3 and 4. Now from second, third and fourth, we have an raised to power 1 by n is between l minus epsilon to l plus epsilon, or we can say an raised to power 1 by n minus l mod value is less than epsilon for all n greater than equal to m. Therefore, we can say that limiting value is equal to L, that is limiting value both is L. Now the second case, when L is infinite, in this case limiting value is infinite, we can rewrite limiting value as this one, and this becomes 0, this is finite. Proceeding as in case first, limiting value of 1 by n raised to power 1 by n equal to 0, therefore this is 0 and this becomes reciprocal is infinity, therefore value will be same in both the cases. Now taking remark, the converse of above theorem is not true in general. Consider an is equal to 2 raised to power minus n plus minus 1 की power n, then an raised to power 1 by n is becomes equal to 2 minus 1 plus minus 1 की power n by n. Limiting value is 1 by 2, and if we divide terms, this value becomes this one. This is when n is even 1 by 8 and 2 when n is odd. Thus this does not exist. Now taking some examples, show that limiting value of square root n plus 1 minus square root n when n tends to infinity is 0. Let an is this one, an is positive for all n, therefore an multiplying this and dividing, what we have value is 1 by square root of n plus 1 plus square root n, which is less than by 1 by square root n. As if we decrease the denominator, then total value increase. Therefore an is between 0 and 1 by square root n for all n, but limiting value of this is 0. By squeeze principle, limiting value of this is 0. show that limiting value of 1 by n square plus 1 by n plus 1 square plus so on plus 1 by 2n square equal to 0. Let an is nth term is this one. If we write this one in denominator n plus 0 square, n plus 1 square, n plus n square, and in every term if we decrease the denominator, terms becomes greater than, therefore this total amount becomes greater than by the previous one. And total sum is n plus 1 by n square, value becomes 1 by n plus 1 by n square. An is less than 1 by n plus 1 by n square, also an is written again in this form. If we increase the denominator, then value becomes less, therefore this value becomes 1 by 4n plus 1 by 4n square. An is greater than by this, marking this as number 2. From first and second we are able to say that an is between 1 by 4n plus 1 by 4n square and 1 by n plus 1 by n square. An is between cn and bn for all n. Cn is here this, bn is this. If we apply limit on this, value will be 0. By squeeze principle, limiting value of this is 0. If a is any real number such that a is between 0 and 1, then limiting value of a raised to power n will be 0. A is between 0 to 1, 1 by a is greater than 1, 1 by a is equal to 1 plus h for some h greater than 0. 1 by a raised to power n becomes 1 plus h raised to power n. By using binomial theorem and taking only two terms, we can say that, and also greater than nh for all n. That is, an is between 0 and 1 by nh for all n. But limiting value of this is 0. By squeeze principle, we can say that this is equal to 0. Now show that limiting value of 1 plus 1 by 3 plus 1 by 5 plus so on 1 by 2n minus 1 by n is equal to 0. Let an equal to 1 by 2n minus 1. Limiting value applying 0. By Cauchy first theorem on limits, we have adding first n terms and divided by n, and when taking limit, that will be also equal to 0, and this is the required result. Similarly, we can prove second result. Prove that limit when n tends to infinity of n raised to power n by n factorial whole power is 1 by n is equal to e. Let an is equal to n raised to power n by n factorial. An plus 1 is equal to n plus 1 raised to power n plus 1 by n plus 1 factorial. If we divide and simplify, we have value as equal to 1 plus 1 by n raised to power n. And if we apply the limit here, value will be equal to e. An is a sequence of positive terms such that its limiting value is e. By Cauchy's second theorem on limits, an raised to power 1 by n will be equal to value limit an plus 1 by an, that is e. Therefore, value will be required as. Taking next problem, show that the sequence n raised to power 1 by n converges to the limit 1. Let an is equal to n. Therefore, an plus 1 by an is equal to 1 plus 1 by n. And if we apply limit on this one, this value give 1. Hence, an is a sequence of positive terms such that its limiting value upon an plus 1 by an is equal to 1. Therefore, by Cauchy's second theorem on limits, the value will be same. Therefore, value will be equal to 1. Now, example number 8. Show that limit n tends to infinity 2 by 1, 3 by 2, 4 by 3, n by n minus 1 raised to power 1 by n equal to 1. Let an is equal to 2 by 1, 3 by 2, 4 by 3, n by n minus 1. Therefore, an plus 1 is equal to increasing one term. If we divide and taking limits, value will be 1. Therefore, by Cauchy's second theorem on limits, value will be the same for these two. Therefore, value is equal to 1. Dear students, try exercise 2.2, and if you have any problem, then discuss with me. Thank you.